Welcome to this lecture series in linear algebra. In this lecture, we'll learn about the notion of orthogonal projections, and let us recall the relevant things. So first, let us recall the notion of a projection in the context of an arbitrary finite dimensional vector space. So let V be a vector space, and suppose V is expressed as the direct sum of two subspaces, U and W. Then the projection on U with respect to W was defined as the map. By notation it is this, and it is a map from V to V, which does what? Which takes a vector little u plus W to U, and this is true for all little u and all little w. Okay, so that's the definition of this guy, and you can, we did everything. So we showed that this is indeed a linear map and well defined and everything. Well definedness is very easy. Linearity is also very easy. So that's the definition of projection on U with respect to W. The picture is very simple. Suppose this is U, this is W, and the direct sum of U and W is the entire vector space. So all you're doing is, if you have a vector here, you are taking this particular component of it. So there is a W component, there is a U component. You just record the U component, and therefore you're kind of projecting on U. So that's the definition. And then if suppose we are given a linear endomorphism, then it is called a projection if there exist subspaces U and W of V such that V is of course the direct sum and P is the projection on U with respect to W. So that is the definition of projection, and the key fact we proved was that P is a projection if and only if this algebraic condition holds. So if P composed with P is P, then it is a projection, and if it is a projection, then P composed with P is P. So that is written as P square. P composed with P is written as P square. Okay. So now let V and W be inner product spaces. So that's so much for projection. Now we are going to recall the notion of the adjoint. So fix two inner product spaces over the same base field, either real or complex, and fix a linear map from V to W. And the adjoint of T was defined as the map T star, which is from W to V, via this diagram. So there is this bijection between W star and W. This is the transpose map. And then this bijection from V to V star. Okay, what is this bijection? Recall, this is just W going to blank W and V going to blank V. And this is the map induced here is the adjoint. That's the definition of the adjoint. And the defining equation of the adjoint is this. So let me make a comment here, which I think I forgot to make. Both are inner product spaces, but we are using the same symbol to denote the inner products on both of them. This is a very common practice. Technically, we should put a subscript here. So this inner product is happening between two vectors in W. So this inner product that we are using is the one on W. It doesn't make any sense to use the inner product on V on these two vectors. So technically, we should have a subscript to distinguish between the two inner products. But since this is not causing any confusion anyway, so it's just better to not use extra decorations. All right, let's move on. Here are some problems for practice. And now let us get started. So we will define what is an orthogonal projection. So fix an inner product space V and fix a subspace of V. the orthogonal projection on U. The orthogonal projection on U is defined as something, but let's first see the picture. So this is U. What you would like to do is, whenever you have a vector here, let's say this is the origin, just for reference, meaning the 0 vector. So whenever we have a vector V, we would like to take the, we would like to drop the perpendicular on the subspace and record this component. So once again, we would like to drop the perpendicular and then record this component. That would be the orthogonal projection of V onto U. So the definition is very simple. All you do is you consider U perp, the orthogonal complement of W, and now take the projection on U with respect to this subspace. And that will, you can just think about it and convince yourself that yes, this is the right definition. So the formal definition is as is. The orthogonal projection on U is defined as the projection on U with respect to the orthogonal complement. That's the definition of the orthogonal projection. So it is basically the map. In notation, it is basically the map P U U perp. That's the orthogonal projection onto U. Okay. We say that a linear endomorphism on the inner product space V is an orthogonal projection. So there is no notion of a subspace right now. In the previous definition, we had a subspace and we defined orthogonal projection on it. Now, an endomorphism is called an orthogonal projection if there exists a subspace U of V such that P is the orthogonal projection on U. Right? So very natural definitions. And now let us prove a key fact about orthogonal projection. So here is the main result that we want to prove. Suppose V is an inner product space and P is an endomorphism on V. And then we have the following characterization of an orthogonal projection. Just like we had a characterization for a projection, we have one for orthogonal projection. So it says that P is an orthogonal projection if and only if these two algebraic conditions are satisfied. The first one asks that it is a projection because we know that this is equivalent to saying that P is a projection, but one needs an extra condition to ascertain the fact that it is not just some arbitrary projection, it is an orthogonal projection. Obviously, the notion of orthogonal projections makes sense only in the context of an inner product space. Alright, and conversely, if something satisfies these two conditions, then it is an orthogonal projection. That is what we want to establish. Okay, so there are two directions, we will do both of them. So first, start with the assumption that P is an orthogonal projection. So there exists a subspace U such that P is the projection on U with respect to the orthogonal complement of U. Okay, so clearly then one holds. We will be proving 2. So to prove 2, we want to show that. Right, this is the thing in yellow is what we need to show to prove that P is its own adjoint. So fix U, V and W and say V is equal to V1 plus V1 prime, where V1 is in U and V1 prime is in the orthogonal complement of U. Alright. Similarly for W, Right. So we have that, and now this inner product is what? This is equal to v1 dot w. Why is that? Because what is p of v? P of v just kills this part. That's the definition of p. Hence, it retains v1. But what is this? This is equal to that, which is equal to that. But what is this? This is equal to w1 is equal to pw, so we have that. But then again, since v1 prime is orthogonal to u, we can write this, but that is equal to v dot pw. So that proves it. Okay, so this implies that. And now for the other direction. So for the other direction, we start with assume 1 and 2, meaning p square is p and p is its own adjoint. Okay. So first of all, we know from this that p is a projection. So let u and w be subspaces. Such that p is the projection on u with respect to w. Right? That just follows from the first condition that such u and w exist. And what we will end up showing is that w is the orthogonal complement of u, which will finish the proof. So claim is, or rather fix, so we'll show that okay. So fix little u in u and w in w. We will just show that these two things are orthogonal, but u dot w is pu dot w, because p of u is equal to u simply because p is the projection on u. When restricted to u, p behaves like the identity map. That's what gives us this, which is equal to, by the definition or whatever, defining equation for the adjoint, we have this. But now we use the condition that p star is equal to p. So we have that. But what is pw? Pw is 0. Right? P is the projection on u with respect to w. So it kills everything in w. So this is equal to 0 and we are done. We have shown that you pick an arbitrary vector in u and an arbitrary vector in w, you get that those two things are orthogonal, giving that w is equal to the orthogonal complement of u. So that proves our main result, and with this I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.